Our next presentation is Navigating the Complexity of VXLAN and IPv6 Migration for Reliable Enterprise Data Centers by Gautam Nilamaitai and Suvik Ghosh. Gautam Nilamaitai is a network engineer with 12 years of industry experience with exposure to healthcare, cloud providers, and large-scale enterprise networks. Gautam has been working at Meta for over 6.5 years, leading efforts to build and operate Meta's enterprise data centers and backbone. I will leave Suvik Ghosh to introduce himself. Thank you.
All right, thank you, everyone. Hey, my name is Suvik, and I've been working in Meta for the last 6 years. Before Meta, I was with Cisco, and throughout my life, I've been doing only data centers. So today, we are going to talk about VXLAN. No, we are not going to talk about VXLAN. Even though the title of the presentation says that it's a VXLAN presentation, however, we'd like you to share some our journey from migrating from a traditional data center to a VXLAN-based data centers. What did we learn? Where we failed? And that's the story which we'd like to tell today. All right, so this is the agenda for today. We want to talk about the drivers which basically prompted us to explore a new option for our data centers. Then, this is the most important part. We are going to talk about the new processes and some changes in the environment which we did, which has nothing to do with VXLAN. And finally, the migration approach which we took to convert our brownfield data centers to a greenfield data centers, and what challenges we ended up with. Even after migrating to this new data centers, we had to encounter some challenges, and we'd like to share those stories with you. Okay. There are two main parts for this presentation. One is we are looking at the very basic issues which were present in our old data centers, which kind of forced us to go to a different kind of a design. And then there was also a problem with our fleet management. That's where all these processes which I was talking about is going to come into play, and we'll share the story. Now, let's start with the challenges. First challenge. Well, we thought that initially our data centers was just like a 3-tier design coming from a classic CCNA Cisco book. Access, distribution, core. Now, we wanted to get rid of a spanning tree, so we thought that we were going to do multi-chassis ether channel. Some call it MLAC, some call it VPC, it has different names. But at the end of the day, we felt that that actually caused more problems than solving the problems. Split brain issues, whenever we try to do a maintenance of a specific router, you know, the VPCs or MCLAC doesn't even come up, so we were really having a hard time dealing with this protocol. Now, since this was an enterprise data centers, in enterprise data centers, one big thing which kind of influences our design is maintaining security. Now, our way of enforcing security inside the data center are mainly can be categorized into two ways, using VLANs plus an ACL combination, ACL applied on a default gateway, or for stateful inspections, we also have combinations of ACL firewalls as well as VLANs. That had some challenges, and I'm going to dive deeper into what those challenges were. Finally, the first introduction of the problems. Now, Meta had a huge growth in a very short span of time. So what ended up happening there was, we did have some sort of a source of truth, but the source of truth was more like a reconciliation of what's there present in the devices. So we configure the devices first, and then based on what the devices have, we build our databases. Ideally, it should have been the other way around. We should build the devices based on source of truth. So that's where the big change in the processes also came in. All right. This was an influence, by the way. So the company also took a direction that we are going to move everything to IPv6. And we were really, really serious about that. And the main reason for that is the most common one, which is IPv4 exhaustion. We tried to do CG-NAT for services inside the DC, but then again, the exhaustion of IPv4 was there for real. Now, with the introduction of IPv6, there were more challenges. Operating system, even today, the fundamental IPv6 implementation, they work differently, and they have different interpretation of what the RFC says. We also had a very funny situation in our data centers where IPv6, we all know, should not be doing any kind of broadcast. But there were situations where IPv6 packets were sent with a layer 2 broadcast frames. So things like that, but the biggest and the major issue was, remember I said that we have this enforcement way of policy using ACLs? Now IPv6, or introduction of IPv6, actually made that problem even worse. Now, for those of you who have a little bit of a background about the TCAMs, IPv6 generally takes double the TCAM space as compared to IPv4. What that means, our already overloaded ACLs became even bigger. So what was the immediate reaction from us? Since the ACLs are bigger right now, we have to start splitting them. So instead of applying it on the default gateway, we now try to move some of the ACLs to the core gateway, extended the services all the way to the core gateway using some sort of a VRF. That was the main idea. And the other big issue was, especially in the data centers, we had this pod concept, and each pod was a layer 2 boundary. It has its own default gateway, and what that means is that now my ACLs problem is kind of widespread. I have to apply this ACLs into all the different pods on their default gateway to maintain my security posture. All right, so the next immediate reaction was to go with a bigger box. That's exactly what we did. We bought a box which can support a bigger ACLs, bigger TCAM, so on and so forth. Now here, excuse me, there is one other thing which I would like to mention here. This pod architecture also prevented us from doing an efficient vMotions. Our compute infrastructure may have an imbalance in terms of utilization of memories and CPUs in one pod versus the other. But since vMotion doesn't really do well across a layer 3 boundary, we could not do a vMotion between the pods. So it was really, really inefficient. So what do we do? Well, the solution was already there. So this is nothing new, and I'm talking about a story which kind of happened 2019, 2020. So VXLAN was already present there. It was an immediate choice of protocol, which we used to make the entire data centers look like a giant L2 domain. Now, since I've already established some of the problems that we had, I'm also going to share with you what are the issues or how VXLAN actually solves some of those problems. First of all, the design itself was like this. We created some principles for us. As Meta, we'd like to stay as vendor agnostic as possible. So the design was created in such a way that it should not matter whether it should work with vendor A or vendor C or vendor J, whatever the vendors are. So our typical design became like this. We have the torch switches, which are right at the rack. They are the leaf switches for VXLAN. Then we have a spine switches, which is creating that logical pod boundaries. Then there is a global super spine switches, which connects all the pod. And everything is layer 3. And also, we also introduce IPv6 underlay. So our underlay is also IPv6. So no spanning tree. There is absolutely no spanning tree here, no MC lag. So we kind of got rid of that initial problem. Since this is all layer 3, we can actually extend the layer 2 across multiple pods. We also had this opportunity to consolidate our ACL layer, which was earlier per pod, now became one single place, right at the top of the core. This is where we consolidated our both stateful as well as stateful enforcement points. All right. From the security point of view, earlier we used to apply ACLs per VLAN. That was our security, definition, as well as each service used to have a specific VLAN for them. Now, when we analyze the data, what we found out is that there are several VLANs which kind of share the same security posture. So we adopted this change where instead of using VLAN as an attribute, now we put all this VLAN into a single VRF and apply the ACL at a VRF level. So that again also reduced a lot of ACL for us. Now, I'll take a pause here. I just want to say that the ACL problem is still not resolved because you see, we have reduced the ACLs, but it's still not at a point where we can say that it's absolutely gone. So we are still buying a beefier hardware, but since we have consolidated the design, we are buying less number of hardwares. We do have plans. We can talk about it in some other conversation, that what is the long-term plan for dealing with this ACL issue which we have. All right, so moving on, this is again a process change, nothing to do with VXLAN. We really took the intent-based approach. Nothing fancy, but just wanted to share how Meta or we did it. So we kind of decoupled the design from the build itself. Giving an example, let's say I have to build data center 1. It's going to have vendor A, and I'm going to build another data center 2, which is going to have vendor C. So what I'm going to do here is I will create a design which has no bearing with the underlying hardware being used. For that to happen, I'll create a hardware spec where this definition of each vendor platform hardware goes in. These are combined together to form this node or logical node which forms a fundamental block of the design. Finally, each data centers will also have its own attributes. One common example is going to be IPv4 or an IPv6 subnet address. Not all applications exist in all the data centers. Maybe it will have its unique application/VLAN definition. So all of them will eventually come together to form the source of truth for that build. Now, this might not give you the full sense of what it is bringing. So what I wanted to do is I wanted to complement this with some of the use cases which this approach kind of unblocked. First of all, it made our config management really, really simple. Since we have all of this information there, we can use this information to build the configuration of the boxes. Very popular use case. The second use case, what I can tell here is, it also made our vulnerability management a lot simpler. So now, since I know that this is a device which is running this version, this hardware, XYZ protocols, ABC subprotocols, if I have a system which kind of gets the information from the vendor regarding what are the vulnerabilities which are newly published, it does a good match whether it's actually applicable for our environment or not, and gives me a good signal that, hey, you may be affected with this vulnerability. There is one other use case which I'm going to talk about a little later. The final, the number 3 changes what we did, we kind of encoded our IPv6 addressing in such a way that it becomes deterministic, and we start building or hiding a lot of information about the rack, the location, the pod inside the IPv6 address itself. So today, if I just go and see an IPv6 address, I can particularly tell you that this comes from this area. So my host location becomes extremely simple, not only for an engineer who likes manual stuff like me, but this also forms a model to our automation system. Troubleshooting, AI, everything picks up on this information and gets this information in a very specific model format. All right. This is the fourth use case. Now that I have a source of truth, let's say some user is trying to put some rogue information, maybe IPv6 address, which doesn't follow a specific subnet mask, or an IPv4 address, which has some mistakes in terms of maybe instead of 5, he has written 25, which doesn't make sense for that specific data center build. All of this will show up. Now, these are getting caught in our validation, and it gives an early signal to the operators that there is a problem there. Journey, I started this in 2020. Then we deployed the first data centers with a vendor A, vendor C, and then we moved on to deploy more and more data centers with other vendors. Then our sister teams also, our partner teams, not sister teams, rather partner teams also adopted this. Now we are leveraging the intent which we created for different designs as well. So all the AIDCs which are being built, they kind of follow the same format in terms of maintaining designs, configuration, everything as a code. Now, next week or end of this week, we're also adopting the same design, same concepts for our enterprise as well. Our office is also going to adopt the same VXLAN-based, the intent-based problems which I talked about. Now, my work was kind of done here. So I deployed a lot of evergreen stuff. And I thought that I have done the hard work. So I'm going to pass on the harder work, which is about migrating the existing data centers to this new design to someone else. I used to manage this person. His person's name is Gautam. Back then, so I said that, okay, I'm done. You go ahead and take care of the migrating the brownfields, which is 100 times more difficult than just doing a greenfield deployment. So I just left the team with one information, that if there is a problem, there is one number to call, and that number is 1-800-GAUTAM. With that, I'll just pass it on to him to walk us through the rest of the presentation. Thank you.
Okay. Thank you, Suvik. So, as Suvik mentioned, we started to transition or build new data centers with VXLAN. But at the same time, we are left with our legacy data center, still running the traditional network. But at the same time, we have our hardware refresh kicking in to replace all the hardware. So, given the ecosystem of applications that we have, which are both containers and VMware like vMotion, VMs, it's not an easy migration for us to do. So we started to reach out to the customers or application owners asking, would you be able to interested moving your application to new DCs? But apparently, no. They wanted to build or take the downtime versus taking the time to rebuild everything in new DC, given that the timelines that they're working on. So we started to explore what are options to do the migration. Now, in this case, when we went and researched on the internet, of course, we couldn't come up with a single process that works for us. And we had given a challenge to do this migration with minimal downtime for all our applications. So for that, we came up with our concept of bridge layer. So bridge layer, on a high level, it's a set of routers connecting the legacy network and the VXLAN network and act as a temporary gateway during the migration. So what are the key requirements for our bridge layer? Sure, it's running the VXLAN with V6 and everything, and of course, adherence to our RFCs. At the same time, we want the operator to be able to log into these devices and execute some Python scripts. Not just any native Python. We want them to able to install third-party packages and execute a lot more logical Python scripts. And once we identified this layer, okay, that this is going to solve our problem, we started to do our collections of all the hosts. With our 80,000 plus hosts in our network, it's tedious work to get information for every host. Is it active? Was it decommissioned? Because it's a legacy host that we've been working for the last 6-7 years, and we wanted to make sure that we have a reliable information. So we started with the first automation where it was collecting all the network data from all these devices. And we fed it to a processor, which also intakes other information from other internal databases, which has information about their on-call and what is the state of their VM, are they pingable, and everything. And it kind of created a new structured data for us that gave not just the network operator, but all the application owners to understand what is being migrated, what was the previous state, are they migrating, are they not migrating, things like that with all our new structured data. We kind of built APIs on that one to understand, like executing a script in particular DC, they will know the status of their application. Once we have all the collections done, now we started to do the network staging. So first, we started to bridge the two networks with bridge layer. And we make sure first with prefixes, all the prefixes coming from the VXLAN are prepended so that the traffic would not immediately go to the VXLAN fabric. Next, we ensure the trunk link going towards the legacy switch has no VLANs allowed on it. And then we enable the gateway on both on the bridge switch, while the other gateway is still active on the traditional network. So at this point, if you look at the whole network, we have both the networks advertising the same set of prefixes, but one is less preferred while the other one is still taking the traffic. And at this point, the traffic is still flowing the traditional architecture only. Now, the magic of the Python, which we're actually implemented on this bridge switch, is using a SCAPI module and continuously running a packet generation for all the gateway hosts, which it identified they're active. Now, in this case, it will go through multiple VRFs or the namespaces on this box and identifies what are the gateway IPs and continuously sends a multicast packet on this interval. In this case, now since there are VLAN is not allowed on the trunk, the traffic is not actually traversing through that link at that point. Now coming to the execution, we kind of, in the first phase, it's a logical migration where we have a connection established to both the legacy aggregation and the bridge switch. And first thing we did, of course, disable the gateway, and that we immediately withdrew the prefixes from the legacy network. And the automation immediately pushes an VLAN update on the trunk. What that does, and at the same time, since the bridge switch is actually sending the SCAPI packets, it was sending the updates immediately, so the hosts were actually updating their MAC address immediately. And with this process, all the traffic actually still shifted through legacy and bridge and through the VXLAN. During this process, I mean, the amount of downtime which we take is like in order of seconds because they're continuously being packets generated to all the hosts to update their gateway MAC address. Now, one thing to want to highlight is the migration is per network basis. It's not like we're migrating thousands of network at one time. It's network by network, it goes step by step, the automation would execute that. Now, once we have all the networks migrated, we're at a phase to migrate the top of rack switches. For top of rack switches, what we ensured ahead of the migration was we made sure the rack switches which are going to be replaced or migrated has to have the right hardware first, and we ensured all the rack switches are replaced. And we used our automation to kind of upgrade the image and immediately have them available. And the bigger feature that we are kind of requested from the vendors is to have the replace functionality, which is critical for us to ensure there is no legacy config and everything is completely replaced with the new VXLAN fabric. And with that, all the traffic started to move in this VXLAN fabric, and we were successfully able to migrate all the applications into VXLAN. So this is a bigger challenge for us to solve the migration. Sure, and we kind of completed it in most of the data centers. Now, it didn't stop there. We have a lot more issues because it's VLAN and VXLAN there. So the first one we started to face issues are with ECMP hashing. So just to give a little bit TLDR on here on this one, IPv6, and there is communication between two hosts. If a host saw it has to do a 3 retransmits, there was a field in a Linux host specifically saying that change the hash or get a new hash into it. So assuming that the path in the destination is actually broken or lost a packet. But it's not always the path. It can be the destination, which is actually slow to respond to the packets. In this case, our host or the destination was kind of slow to respond packet, and it caused issues to any stateful anycast addresses. For that one, we have a couple of options. Either we fix the hashing. Now, coming into this one, to go a little bit deeper details, previously on the network, it was L2 domain. And the hashing is based on L2 headers. But when we transition to VXLAN, it's L3 headers. Now we have more fields, IPv4, IPv6, and flow label in some vendors. And so the consistency of the hashing parameters are not consistent across multiple platforms. And it's something that we have to either ensure while building it, or the other approach is disable IPv6 hashing on a packet trace transmit. So given the state of our network, we didn't want to change the hashing because how the ECMP is working fine for us. So we went with an option to disable aggressive hashing on this. Next one, convergence delays and drops. As the networks grew bigger and bigger, we started to have, of course, a lot of the VXLAN routes, and it's stable for a while, but when we started to get a new code recommendations and we wanted to upgrade these devices, especially in the top of rack switches, we started to see disruption to the services. Going into a little bit details, like a server, when it saw a NIC up with a rack switch, it just immediately polarizes the traffic onto that interface, and assuming that everything's on the upstream is working fine, but it's not really. Like there's a lot of BGP happening on the top, doing a lot of reconvergence, and it took some time for the whole thing to happen. And during this time, when the server is sending the traffic, it's actually black holing all of them on the device. What are the couple of options? I think we just with one option here. We started to track the BGP sessions with the super spines, I think from the previous diagram, and we ensured the BGP sessions are up and stable based on our convergence time, and set the delay to turn off those interfaces to certain minutes, so that the server would not immediately send the traffic out to the switches once they're upgraded. Second one, not second, the other one is BGP peering with the gateways. So coming from, again, traditional network, we have a lot of hosts doing a BGP peering with our aggregation layer to advertise some of these NACAS prefixes. Now, when we move to the VXLAN network, and with a symmetric IRB, the gateway being everywhere on the rack switch, the peering was established with the gateway. But it's causing a lot, and there's another automation on the compute side of folks where they would move the VM silently from one server to another server, and which is a hot move. And in this case, there is no TCP session break happening. They just move to a different rack, and the session which happened with the other tower was continuously advertising the prefixes when they are until the keep alive timer expired on them. And with that, we are left with a couple of options. The first one is either disable the host mobility, which it didn't make sense because they wanted to balance the capacity from one compute server to another server automatically, and we don't want to block them. In this case, we wanted to take a different approach. They will be able to support any chaos gateway and the centralized gateway indices. Now, the other one is neighbor discovery. As I mentioned in the previous slide, when we did all the collections, we noticed that, okay, we got these set of networks are using Slack, or we are using certain parameters, and we didn't kind of configure any lifetimes on them. It worked at that time, but when we transitioned to another vendor, the lifetimes are varying by default. In this case, when we try to have new hosts connected to it, they never are able to establish IPv6 connection because the timers are different. And for that case, we kind of went with more static values for every network that we wanted to configure. Now, what this enabled is for future. This is not directly related to the VXLAN or IPv6, the way how we approach the things to solve our for future needs. Now, once we have all the intent built, and This is something a service spec would look like, which for a VLAN, what is a network, what is a security zone, what is the firewall type, and everything. Previously, when we used to do a storm, it used to be a storm per data center, which is a lot more chaos with number of applications, how they're tracking the on-calls, the issues, and everything. It's a lot more chaos there. So we started to go little bit more granular. And with this thing, we're able to give an operator a click of a button to either storm that VLAN in that particular DC. It would just go and shut down the VLAN or that network and able to migrate. It's not just the DR engineers. It gave the opportunity for app engineers to test their resiliency as well. Now, other thing, as we move more and more into the intent-based, we have another thing called enforcer. It's something similar to intent-based, where our automation was actually collecting all the MAC addresses that it is learning on the network, and at the same time validating the databases that the MAC address is actually supposed to be there on the network or not. And not just the MAC addresses validation, but it is also verifying the host status. Like if a host is currently running a certain image, is the image currently compliant or not? And things like that would identify a bad host, and an automated push would go in and identify the MAC and push the changes to the network layer to disable all the rack switch, to block the traffic from that MAC anywhere. Since mobility can happen, we were putting like across the fleet for that MAC address. And at the same time, as we saw in the journey, the demand actually came in for AI data centers. Leveraging the intent here, we were able to use the same 5-stage clause network, and at the same time use the hardware spec and the edge spec and the node spec and multiple things that are involved in the intent, and it made us quickly jump on to building new data center demands and stuff like that. Now, coming for the key takeaways from this presentation, first one, simplicity is the key. VXLAN is everywhere, and there are a number of architectures you might be seeing on the network and on the internet. And when we approached all of them, we wanted to keep it as simple as possible. It's not just us, it's not for the engineer. We want the operations team able to understand and manage our network. So when we build this whole thing, we ensure the network is scalable. At the same time, the VLANs, VNI, everything, all that information are in sync or with automation, all that stuff. Now, the second one is deterministic approach while designing IPv6 networks. As we saw in the previous slide, where we try to encode a lot of region or information into the IPv6 address, it's not just information about the network, but it's also information about the location and everything. It gave us automation, a lot more run to validate and verify things at that point. And establish a good ecosystem. In this case, again, the source of truth plays a critical role in our ecosystem. Like where the VLAN, when a VLAN is being reserved and the right VNI being tagged and all that stuff, we maintained automation again. Like a new reservation would go with all this information into a database, and it is managed through like peer reviews and stuff like that. And one bigger thing is zero delta config. When we have this huge fleet of devices, we don't want to maintain any snippet of configs that are like snowflake. It's hard to manage. There can be like a hack or anything. We wanted to make sure the configs are in sync with what we want it to be. So build an ecosystem that can have a zero delta in the config that you wanted to have. And coming to the host provisioning, as we build more and more data centers and more applications, the provisioning team, at least in our side of things, they felt static allocation provided much more deterministic approach compared to DHCP and Slack. But it can be varying per cases, but in case of Meta, our provisioning went with static IP allocations for kind of host tracking. And IPv6 subnet planning. When you see an IPv6 network, of course, you can see like, you can build thousands of hosts. Like it's not like an IPv4 network. And it can easily throw us into a different path where, in our case, the TCAM issues and everything can arise when you have a prefix greater than a /64. So ensure our suggestion was to maintain networks at least 64 and don't go beyond that. And the aggregation, when the data centers are growing and growing, the IPv6 networks R will grow and the number of prefixes will grow, and aggregation is going to play a key role for us. And configuration consistency is the key. Given that we are running kind of on a symmetric IRB, we wanted to have a consistent config across the devices for any specific network, because one specific node with a different config can throw, or because there will be headend replication and the traffic will be going to multiple rack switches, and they can have issues with other hosts if one host has a bad information about the gateway. I think at this point, I'm done with my information, but I'm happy to take any questions from here.
There's a question.
Yeah.
Hey.
Jared Cordova from Nokia. Quick question. So we talked about the migration process and how you guys built everything on an intent. What did the process look like after going through the brownfield of mapping those changes to the intent and having to rebuild that?
What is the process, or?
Yeah, so how did you, in an intent-based automation approach like this, right? You have an overarching top-down intent approach. If you're going from brownfield, then you're going bottom-up. So how did you guys rebuild the intent to match the newly created configs for those tours?
So I think on one of the slides where the collection is happening, we actually went to every host and restructured converted everything to an intent. So the automation is completely doing that piece, understanding the network, identifying the slack like any parameters that are configured for the network, and converting into an intent. So it was building this whole intent in the whole aggregation piece. Not just for the migration, it gave us a lot more stuff into intent as well. Yeah.
Yeah, just to make that answer simpler, back in the days, we never had intent.
Yeah, we never had.
So we redid the intent for the new portion of the network, if you remember the green portion of the network, and then moved everything to the green portion. So we did not really use intent to enable the migration, but the intent portion actually came handy after the migration, if that makes sense. Any other questions? All right, thank you. Thanks, everyone. Have a good one.